In the winter of 1967, deep inside Ford's engineering facilities, a group of men stood around an engine that wasn't supposed to exist. No press releases, no brochures, no public testing, just raw aluminum, cast iron, and a design so extreme it bordered on insanity. Most people have no idea this engine ever existed, and even fewer understand why Ford built it in total secrecy. Because this wasn't just another racing engine, this was a weapon. But what almost nobody knows is, it nearly destroyed everything Ford had built in motorsports. And what happened next changed everything. To understand the tunnel port, you have to go back to a time when horsepower wasn't just a number, it was a battlefield. The late 1960s were chaos. NASCAR, drag racing, endurance racing, everywhere you looked, manufacturers were locked in an all-out war. Ford had already tasted victory with the 427 side oiler, a brutal iron block monster with a 4.23-inch bore and a 3.78-inch stroke, displacing 427 cubic inches of pure American aggression. In race trim, it could push well over 500 horsepower. Torque? Around 480 lb-ft, enough to twist drive shafts like pretzels. And yet, it wasn't enough, because Chrysler had just dropped a bomb. The 426 Hemi, with its hemispherical combustion chambers and massive airflow potential, it was dominating NASCAR. Drivers were reporting higher RPM ceilings, better breathing, and more consistent power delivery at speed. Race after race, the Hemi was leaving Ford teams in the dust. And it wasn't just about raw power anymore. It was about efficiency, about breathing, about getting every molecule of air and fuel into those cylinders as fast as physics would allow. Ford's racing division was hemorrhaging wins. Engineers were working around the clock. Team managers were getting desperate calls from Dearborn headquarters. The pressure was mounting because in the 1960s, racing wasn't just marketing, it was identity. It was national pride. It was everything. Ford had a problem, a big one. So they asked a simple question. How do you beat an engine that breathes better than yours? And the answer they came up with was extreme. Instead of refining the existing design, Ford engineers decided to completely rethink airflow. They didn't just want better breathing. They wanted maximum airflow at any cost. They locked themselves in the engineering labs. They ran calculations that would make modern computer simulations look simple. They sketched, they argued, they threw out decades of conventional wisdom, and then they started building. So they built something radical. The 427 tunnel port. At first glance, it looked like a normal FE Series V8. Same basic architecture, same 4.23-inch bore, same 3.78-inch stroke, same 427 cubic inches. But inside, it was a different animal entirely. The intake ports were enormous, not just big, absurdly big. So large, in fact, that the pushrods couldn't go around them anymore. Traditional overhead valve engine design had always routed pushrods around the intake ports. It was just how things were done, how they'd always been done. But Ford's engineers looked at that limitation and said, what if we just don't? So Ford did something no one else dared to do. They ran the pushrods directly through the intake ports, literally through them. Metal tubes were cast into the ports, creating what looked like tunnels, hence the name tunnel port. It was a solution that prioritized airflow above everything else. The ports were almost perfectly straight, allowing air and fuel to rush into the combustion chambers with minimal restriction. Where conventional engines had curved, twisted intake paths that forced air to change direction, losing velocity and creating turbulence, the tunnel port had highways. Direct routes from carburetor to cylinder. The engineering was audacious. Some called it brilliant, others called it reckless. Both were right. At high RPM, this thing could breathe like nothing else on the track. On paper, it was a masterpiece. With dual 4-barrel carburetors, high-lift camshafts, and compression ratios pushing 12.5.1, the tunnel port was capable of over 600 horsepower in race trim. Some estimates even push that number closer to 650, and it could rev higher than the traditional 427 side oiler, past 7,000 RPM in some configurations. Engineers reported test runs where they pushed it even further, towards 7,500 RPM. The sound alone was unlike anything they'd heard from a big block before. A high-pitched scream instead of the usual deep roar. For a big block V8 in the 1960s, that was insane. Dyno tests showed incredible peak numbers. At full throttle, with the engine singing at 6,500 RPM, it produced power curves that made even hardened engineers step back in disbelief. The airflow numbers were astronomical. Everything they'd hoped for on paper was translating to reality. For a brief moment, it looked like Ford had done the impossible. But there was a problem. Actually, several. At low RPM, the engine was a disaster. Those massive intake ports that worked so well at high speed became a liability at lower speeds. Air velocity dropped. When air moves slowly through oversized ports, it doesn't atomize fuel properly. It creates dead zones. Fuel droplets fall out of suspension and puddle in the manifold instead of making it to the cylinders. Throttle response was sluggish, unpredictable. Drivers described it as dead below 4,000 RPM. Imagine hitting the throttle, and nothing happens. Then suddenly, all 600 horsepower hits at once, like flipping a switch, like going from zero to chaos in half a second. It wasn't just hard to drive, it was dangerous. Test drivers at Ford's proving grounds reported near loss of control moments during acceleration tests. The power band was so narrow, so peaky, that it required constant vigilance. You couldn't just mash the throttle and go. You had to keep the engine in a very specific RPM range, or it either did nothing or tried to kill you. And then the real nightmare started, the valve train. Because the pushrods ran through the intake ports, they had to be enclosed in thin metal tubes. These tubes disrupted airflow slightly, but more importantly, they introduced heat and stress into the system. The pushrods were now sitting in a path where superheated air and fuel were constantly rushing past at incredible velocities. At high RPM, the valve train components were under extreme pressure. Lifters wore out quickly, rocker arms failed, pushrods bent. The thermal expansion alone caused tolerances to shift in ways engineers hadn't fully predicted. One mechanic reportedly said, "It sounded like a bag of hammers after a few laps." And then there was lubrication. Even though the base was derived from the side oiler, which fed oil directly to the crankshaft first, the higher RPM demands of the tunnel port exposed weaknesses. The oiling system that worked perfectly fine at 6,000 RPM started showing cracks at 7,000. Oil whip in the crankcase, aeration in the pan, pressure spikes and drops that the relief valves couldn't compensate for fast enough. Oil pressure fluctuations became a serious issue during sustained high-speed runs. Bearings showed signs of excessive wear. Journal surfaces that should have lasted an entire race weekend were showing scoring after a single session. In some cases, engines would lose pressure mid-race, and when that happened, it was over. Catastrophic failure, seized bearings, broken rods punching holes through engine blocks, oil smoke billowing across the track. The kind of failure that didn't just end a race, it ended entire engines. At events like the 1967 NASCAR season, Ford teams began experimenting with the tunnel port. On qualifying runs, it looked unstoppable. Faster lap times, higher top speeds. Engineers watching from the pits were seeing times that shouldn't have been possible. But in actual races, engines failed. Drivers struggled to control the power delivery. Coming out of corners was a nightmare. You needed high RPM to make power, but high RPM coming out of a tight turn with the wheels turned meant spinning out. Drivers had to develop entirely new techniques just to keep the car pointed straight. Reliability became a constant concern. Teams would qualify well, start strong, and then 15 laps in, 30 laps in, something would break. A lifter would collapse. A pushrod would snap. Oil pressure would drop. And another tunnel port would be pushed back to the garage, its potential unfulfilled. Ford had sunk enormous resources into this project, secret budgets, overtime hours, the best minds in their engineering department. You can probably guess what happened next. But the truth is even crazier. Ford had built an engine that was too advanced for its time, too specialized, too extreme. The tunnel port worked beautifully in a very narrow window. If you could keep it between 5,500 and 7,000 RPM on a high-speed oval with long straightaways and gentle corners, it was a monster. But real-world racing wasn't that simple. There were tight corners, slow sections, moments when you needed torque down low, and the tunnel port just couldn't deliver. Instead of dominating, it exposed a fundamental truth about racing engines. Power means nothing if you can't use it. So Ford made a decision. They pulled back. Rather than continuing to push the tunnel port, they shifted focus to a more balanced design. Something that could deliver strong airflow without sacrificing drivability or reliability. Engineers took the lessons learned, the data on port velocity, on airflow optimization, on valve timing, and applied them to more conventional designs. That's when they developed the 427 medium riser and later the high riser configurations, which optimized port size and velocity without going to the extremes of the tunnel port. These engines still breathed well, they still made power, but they also worked at low RPM. They lasted entire races, they could be driven by mortals, and eventually, they moved on entirely. The tunnel port quietly disappeared. No major victories, no championship legacy. Just a handful of engines built, most used in limited racing applications or experimental programs. Some went to drag racing teams who could use the narrow power band on a straight quarter mile. A few ended up in private collections. Most were simply disassembled, their parts scattered. It became a ghost, a whispered legend in Ford's engineering halls, the engine that almost worked, the one that showed what happened when you pushed too far. But here's the thing, its impact didn't disappear because the ideas behind the tunnel port, maximizing airflow, straightening intake paths, prioritizing high RPM performance, those concepts didn't die. They evolved. You see them today in modern racing engines, in high-performance cylinder head design, in the way engineers think about airflow and efficiency. Every time a modern engine designer straightens an intake port, optimizes flow dynamics, or pushes RPM limits, they're walking a path the tunnel port engineers carved out decades ago. The tunnel port wasn't a failure. It was an experiment pushed to the absolute limit. And like many extreme ideas, it showed exactly where the edge was. By the early 1970s, everything changed anyway. Emissions regulations tightened. The Clean Air Act forced compression ratios down. Insurance companies started crushing performance car premiums. The muscle car era was ending. High-strung race engines like the tunnel port had no place in the new world. Ford ended production of the 427 FE series soon after. Tooling was scrapped. Blocks were melted down. The foundries moved on to making Econobox motors and truck engines. And just like that, one of the most radical engines ever built was gone. Today, original tunnel port engines are incredibly rare. Collectors hunt for them. Engine builders study them. A genuine tunnel port head can sell for thousands of dollars, if you can even find one. Museums want them. Historians document them, not because they were perfect, but because they were bold, because they dared to ask, what if we ignore everything else and just chase airflow? And then they actually built it. That's what makes this story so wild. Ford didn't just build a secret engine, they built a glimpse into the future and discovered its limits the hard way. They learned that racing isn't just about peak horsepower, it's about usable power, reliability, drivability, all the unglamorous things that don't show up on a dyno sheet but determine who crosses the finish line first. In the end, the 427 tunnel port didn't win the war, but it changed how the war was fought. And sometimes, that matters even more. If you enjoyed this story, let me know what you want to see next. Another forgotten engine, another rivalry, or another piece of automotive history that almost nobody talks about. And if you're into deep dives like this, make sure to subscribe, because the next story might be even crazier.